In this lecture, I'm going to review every single skill, one by one, that we have to have for the introduction to the energy test for Regents chemistry. Okay, so here we get started with the first skill. And the first skill just says that energy exists in many forms. What that means is we can go from, let's say, chemical energy, which is often called potential energy, but mechanical energy, okay, like the energy that's in the bonds of, say, propane, can be used to give off heat. That heat can boil water and cause physical motion in a steam engine that I've shown you, a mechanical energy. And that mechanical energy can be converted to electrical energy. Okay, as we saw the generators work by moving. In any case, we're showing you this because we can convert from one form to another. There is no additional energy being made or no additional energy being destroyed. So energy is neither created nor destroyed. It is just transferred from form to form. Okay, in fact, in our calorimetry experiments, we noticed that energy is released, let's say by the burning Cheeto, and absorbed by the water. Now, in truth, it's also absorbed by other things, the air, okay, the glass, the thermometer, but generally speaking, if we measure all the energy released and if we're able to measure all the things that absorb it, this Q, or joules, would be the same as this Q, because energy is neither created nor destroyed, it is conserved. So look at the example I gave you with the skill. So skill 1 is talking about the conservation of energy and that energy can be in many forms. So here's an example of a Regents question with that. As electrical energy is converted into heat energy, the total amount of energy in this system remains the same. We're not creating energy. We're not destroying energy. I know that we're converting from one form to another, but the total has to stay the same because of conservation of mass. Okay, moving on to skill 2. Something like that. Heat transfers of energy, usual thermal energy, from a body of higher temperature to a body of lower temperature. Thermal energy is the energy associated with random motion of molecules and atoms. So there's a standard if you like it. But we know that energy goes from a lot of motion to things that don't have a lot of motion. And the answer why is because things with a lot of motion, a lot of energy, are going to catch up to the things that have less motion. So as you've learned, heat flows from hot to cold. Cold does not flow. So if you look at the example that I have down here, solid X is placed in contact with solid Y, heat flows from hot to cold. Knowing that temperature is a measure of motion, fast motion is going to catch up to the slow motion. So who's the highest temperature? To the lowest temperature. Well, we can go choice A is the answer because 10 degrees Celsius goes to the lower temperature. B is not the answer because low goes to high. Slow moving molecules will not catch up to fast moving. Same thing with this one. This is cold to warm. So that for the same reason. And C, temperature is not changing, so there's no flow of heat. And E, there's no choice there. So that's how that works, and that's an example of skill number 2 and a question from skill number 2. Let's go on to skill 3. Temperature is a measure of the average kinetic energy of the particle in a sample of a material. Temperature is not a form of energy. Yeah, we should know that temperature is what? An average of the motion, or the average of the kinetic. All right, I can do that. Kinetic energy. Motion energy, it's the average. You can't have all molecules moving at the same speed. Some will move slower than others, so temperature is an average. And we looked at the Boltzmann distribution graphs, and we know that when something is warmer, okay, we know that there's more molecules going faster. So let's look at an example of skill number 3. Understand that temperature is an average motion. It's not an energy form, okay? And knowing it's the average kinetic energy. And look at the kind of questions you'll see at the Regents level. So when a substance is made of particles Which substance is made of particles with the highest average kinetic energy? I have seen people get this wrong for many years, and all they're asking for is the highest temperature. Okay, I guess I'm missing the gas here, but it doesn't matter. I don't care what phase I'm in. People might say, well, it's a gas, so maybe it goes faster. Okay, but no, I'm looking for the highest temperature. Don't let the more energetic phase fool you. It's not about the more energetic phase, it's about just the highest temperature. So that's why B is the answer there. Okay. Skill 4. Distinguish between heat energy and temperature in terms of molecular motion and amount of matter. Okay, well, heat energy is a measure of the collective, let's say, motion of all the particles, but we can't really measure that. All we can measure is a change from one form to the other. Temperature, of course, is the average motion. As we just learned, it's based upon not the size of the sample. An average does not matter, or it is not made depending upon how many you have. For instance, you can have an average of 80 in a class, and you can have an average of 90 in a class. Do you need to know how many you have? No. So temperature is a measure of the average kinetic energy. So if you look at the choice or the question here, which beaker would have the particles the highest average kinetic energy? They're not asking for the total energy. That's a mistake many people have. They think, well, the bigger sample, okay, is the one that's going to have more energy. And you're right, but they're not asking for total. They're looking for the average. So they're looking for what? They're just looking for the highest temperature, which is independent upon how many you have. An average is not made by how many. So my friends, in chemistry, we look at the highest temperature, and 30 degrees Celsius is the highest temperature. It's that simple. Okay, skill number 5. Convert Celsius degrees, I guess, to kelvins and Kelvin to Celsius degrees. The reason why Kelvin doesn't get a degree because it borrows the Celsius scale, as we've learned. And let's just do this quickly. Celsius made a thermometer with 2 fixed points. He used the freezing point of water and the boiling point of water. You notice those temperatures didn't change. He put a 0 for the freezing and 100 for the boiling. That's why it's a centigrade scale. That's why the numbers are pretty, because he made them that way. And Lord Kelvin didn't like the scale in the sense that, well, 0 should mean 0 motion, since temperature really is reflective of how much motion. So he found through an experiment that we're going to do that the coldest possible temperature was negative 273 degrees Celsius. He made that 0, borrowed the Celsius scale, put this as 273, and made this 373. And because of that, Kelvin is equal to the Celsius plus the 273 degree difference. He started the Celsius degree system 273 degrees sooner, or before the 0. Now, if you don't like any of that, this is given to you in table T, so just plug it in. So here's the skill. You must be able to convert. So if I have negative 13 degrees Celsius, that goes in here, and I want kelvins, I just add 273 to that. You put it in your later of calc and you get 260 kelvins, which is choice C. No big deal. And another example, what the temperature of a sample of a substance, I can speak, changes from 10 degrees Celsius to 20 degrees Celsius. How many Kelvin degrees does that change? Well, before you convert this to Kelvin and this to Kelvin and subtract, because they wanted to know what? How many Kelvin degrees does the temperature change? Change to you should means, oh, subtract. Think with me for a second. A Kelvin and a Celsius are the same scale, except that Kelvin starts 273 degrees sooner. Okay? So that's why Kelvin doesn't have a degree like Celsius does, because its scale, its degree is the same as the what? as the Celsius. So a change in Celsius, 20 minus 10, is 10 degrees change in temperature, would be the same for kelvins. Change of temperature is 10 kelvins. Why? Well, if you really want to see, 20 plus 273 is 293, and then 10 plus 273 is 283. You'll see that you still get what? 10 kelvins. Because a Kelvin and a Celsius degree are the same size. They use the same scale. So the answer, of course, is choice B. Skill number 6. Distinguish between endothermic and exothermic reactions. We spent plenty of time using energy terms in a reaction equation. All right. So consider the reaction. All right. Looks like they didn't give me a reaction. Okay, it's not written, but let's just make one up. Let's make A plus B gets me C plus energy. What does that mean? Well, the energy is on the what side? It's on the product side. So therefore, it's exothermic, and I'm releasing energy with a Y. Okay, so choice D. So yeah, they would give you a reaction, and you have to notice where the energy, if the energy is on the product side, that means you're producing energy and energy is exiting. And if energy is exiting, exothermic. Okay, number 6. Well, let's take it what? Energy plus A plus B makes C. And by noticing it is the energy is on the what? On the reactant side, that tells me there is a net change of energy. That energy is going into the system. In order for the reactants to react, they need to absorb energy. So I know that the energy is being absorbed. So it's definitely endothermic. This potential energy stuff is another skill, but let's go over it. If it's endothermic, that means that you're starting low and going high because you're absorbing energy. So A and B are reactants, and they would start low, and because they're absorbing energy, their overall energy goes up, they become C. So the potential energy of the reactants is lower than the potential energy of the product. And I guess I could say that as well. The potential energy of the reactants is the same. No. So in this case, I have two choices. I guess I should have made this the endothermic, exothermic. But yeah, but this has two choices. In truth, this question, although I'm guessing, is probably made for an endothermic one. Okay, an exothermic choice. But it doesn't matter. Okay, so yeah, so in this case, there's two choices. I was after just the easy one here. We'll get to this stuff again. So in this case, the way that I wrote it, choice A and C, if I was to write it A plus B going to C plus energy, okay, now being exothermic, I'd start high and be unstable, and I would go down in energy. How would they do that? I'd release it, then I'd be exothermic. And the potential energy of the what? Products, right? I'm going down. Here's my products. Would be lower than the reactants, and there's no choice there. Okay, so this question was made for exothermic, but hopefully you can see that. All right, skill number 7. Explain phase change in terms of the changes in energy and intermolecular distances. All right, well, phase changes. As I told before, solids barely move. They have a crystal lattice arrangement. So they just vibrate in their fixed positions, little vibrations. You give them some heat, they become molecules that are free to move out of this three-dimensional arrangement called a crystal lattice. If you give them even more energy, they overcome their attractive forces and they fly and become a gas. Okay? So a solid has the lowest energy, a liquid is in the middle, and gases have tremendous energy. In order to go to go up in energy, gas is having the most, energy has to be absorbed along the way. So now this question is saying a release of energy. Now, if I'm releasing energy, that means I must be going down in energy. So I must be going from a movement from high energy to low. Look at your choices. Solid to a gas. Well, solid to a gas would require energy to go up. Solid to a liquid. Well, that would require energy to go up as well. Look at choice D, liquid to gas. That would also require energy, so that's why C is the answer. A gas going back down to a liquid, which by the way is condensation, has to be exothermic, because if you're going from a state of high energy to low energy, you have to release your extra energy to get low. These other choices were going up, which means they needed energy. So choice C was the answer. Second example of choice C, which particle diagram best represents a liquid state? All right, well, if you look at your choices, here is a solid because it's got that regular repeating crystal lattice arrangement, and these things only vibrate in their fixed positions. Here you don't have a crystal arrangement because they have what? More motion, more energy. But they're still stuck to themselves. And here you've got things that are able to fly around out of the container. Gas is flying out of the container because they have the greatest amount of energy. Gas! Now this is a diatomic gas, this is monatomic. But the one in the middle is your liquid. Okay? So you should know from the standard who a solid, liquid, or gas is based on their what? Energy. Based on their kinetic energy, which is based upon what? How much motion you have. Gases have more motion than liquids. Liquids have more motion than solids. Solids in that very stable crystal three-dimensional pattern. Whoa, what happened there? So skill number 8. Energy is released or absorbed during a chemical reaction, can be represented by a potential energy diagram. So we draw high going to low, reactants becoming products. Okay? That's a potential energy diagram. The reason why we use potential energy is because we're talking about the energy that's stored in the bonds. If you're stable, you have lower energy. If you're unstable, like the guy in New York City that you don't want to make eye contact with, has high energy. High energy, unstable, remember this is a measure of energy here, the higher one. So if you're unstable with high energy, you're going to do something, like react. If you're stable, you're not going to do anything. You have low energy. So in any case, I have this reaction. Notice the energies on the product side. Product side is after the arrow. I'm producing C in energy. Why am I producing energy? Because energy is being exiting. It's releasing. Okay, so I'm looking for exothermic. Now, if it's exothermic, I'm starting with something with high energy, and I'm going down to low energy. And the change, which we use sometimes as delta H, the change of the heat, is going to be negative to show that energy was released. We went down. So look at your choices. Which one is going high to low? Choice A goes high to low, and so does choice D. But wait a minute, A and B are reactants. It should start A and B on top, that's why, and C goes lower. Don't worry about the little doohickey on top there. And of course, this one looks good too, but it's C. This is your products. You have to have A and B as your reactants. So the best choice is A here as a Regents question. These two would be endothermic graphs, okay, or potential energy diagrams. Example 2. Which of the following statement best describes the characteristics of an endothermic reaction? Well, if it's endothermic, think about drawing diagrams. I always say draw. Well, if it's endothermic, that means I'm absorbing heat or consuming heat. If I'm absorbing heat, I'm taking heat into the system. I must be going up in energy, up in here. So my energy is going up, which means my delta change of heat must be positive. If you forget what the signs are for endo and exo, Go to the bottom of table I. Table I will tell you that a negative sign is exothermic. But I want you to understand, if you're taking on energy, that means you're going to go up in energy. And your delta H is positive, showing it's going up. So delta H is positive. And now if it's positive and you're going up, the products have more potential energy stored in their bonds. So exothermic, start low, goes high. The products have more energy than the reactants. That's why A is the answer. The next example of skill. Energy is released as screaming to you exothermic. When two bonds form. If it's exothermic, you're starting with something unstable and you're getting stable and you're going down. That's why your delta H is negative. But if you're going down in energy, okay, are you creating something stable or unstable? Well, low in energy is stable. So you're creating something stable. All right? And the potential after bonding is going to be lower and stable because you released energy exothermically. Your energy drops and you become stable with low energy. That's what choice D is the answer. Skill number 9, and this is the thing we've been working on the most, is calculate the heat involved in a phase or temperature change. All right, so they're giving me grams, they're giving me a temperature change, and I know specific heat. From table T, I know Q is equal to MC change in T. So I've got 10.0 grams. Specific heat is 4.18 joules per gram per degree Celsius from table B. My change in temperature, 15.5 minus 14.5. Okay, gives me 1.0 degrees Celsius. And I think I can do this math. Grams cancel, degrees Celsius cancel. 10 times 4.18, okay, times 1 is going to be 41.8 joules. Question is the water releasing or absorbing? Well, understand the problem. We have 10 grams of water, and we know we started at 15.5, but wait a minute, the temperature dropped. So that must mean that the water was what? Losing heat to maybe its surroundings, or the cup, or your hand. So for temperature to drop, that's why it's good to draw pictures, the water released that energy. This formula does not measure whether you absorb or release. It just measures the change. You've got to see what's occurring in the problem. What helps you is drawing. Obviously, I expect you to be able to calculate for mass and change in temperature and or final or initial temperature, and I have a separate video that I posted just for these types of questions. So these are the basic skills you have to have. Hope that broke it down nice and easy for you.